crystal structure first, which means that three-dimensional crystal structure as an introduction to the surface structure which we're going to talk about today. And we mentioned a few examples and we discussed the density, for example, the surface density. If you're just looking at one plane on your bow structure, and we also consider the other parameter, which is the interlayer spacing between these planes that make up the whole unit cell of your three-dimensional bow crystal like this. Okay, so the idea was that the plane with the most surface atoms, right? The denser the surface, the more stable is the surface. So if you have more atoms on this plane, then you expect that this plane will be the most stable. Okay, so that's a kind of a general rule that we discussed last time, and we were sorry.
I just have one question about that. So you were talking about the plane surface density being a certain value,
Yes.
right?
Yeah.
But in the kind of reciprocal planes, that value will change depending on where you are within the cube structure, right?
Right. Okay. So the question is that what happens if you go down into the layer, right? The surface density of the layer. The answer is that it should not change.
Okay.
It should not change because if you let's see. We can take an example. For example, this one, right? Let's say you look at this plane. This plane, the surface density of this one is 2, right? Because you have 4 corner atoms. Each of them is part of the unit cell of 4 unit cells, right? And plus 1 in the middle, right? And then if you look at one plane below, this is still in the same orientation. So they will have the same destination, right? Let's say we call this 100 plane. This is 100 plane. If you look at this one, for example, the middle plane that you have 4 atoms. Each of them contribute half, right? So then the density of the 100 plane remain the same. So even if you cut here or cut here, it does not matter. Okay. So that's why it's a good question, because that's why people like to look at this, because the density would not vary with this how you cut your plane, as long as it has the same orientation. I want to see if I can turn on some light. Okay. So that's one consideration about the density, and the other consideration is this d-spacing. As I mentioned before, last day, d-spacing, you will see different effect, because as you terminate your three-dimensional object at this plane, for example, the atoms in the first few layer is going to readjust itself, because suddenly you lost a lot of forces on this side of the crystal, right? Because the symmetry no longer works. So this direction of symmetry. So what will happen is that the layer will adjust itself, and therefore the d-spacing will change, and by a small amount. So for example, in nickel, there's a 7% expansion in the layer. In other words, this d-spacing is 7% larger than the d-spacing inside the ball, okay, in the same direction. Okay, so that's what we meant. And aluminum is even worse. Aluminum is 15% expansion as you go through. You can also have contraction as well. The d-spacing could become smaller than the bow itself. And if this d-spacing, this reconstruction in the d direction could depend on the plane. It could depend on which direction you're talking about. and it depends on the nature of the material that you have. Okay, so that's one of the point. And the other thing is that, so you have reconstruction in the D direction after you terminate this, cut this bulk material, create the surface. Obviously, you also have reconstruction in the plane itself. In other words, the atom itself can move around from its natural position in the bulk. And so that's another reconstruction. So there's both that direction reconstruction and as well as this XY or lateral reconstruction inside the plane, inside the surface that you have. Okay? So there was, so we have, so we point out that these surface density, which is important because of the stability of the surface itself. We point out layer interplane spacing. Due to reconstruction, they could change. We point out reconstruction in the XY direction. 3 point. Yes, there's a question.
In the third diagram, how do we visualize D here?
Yeah, so the question is that in this diagram, how do we visualize D? All you have to do is that you have the triangle here, that's one plane. The other triangle is the dashed line. So the plane immediately parallel to the red triangle will be the next plane. So the D spacing will be the perpendicular spacing between the layer. Okay? So it's often difficult to try to visualize something on two-dimensional, a three-dimensional object. So this is one plane, and this dotted line connect the second plane. And so the spacing, perpendicular spacing, shorter spacing between them will be the D spacing. So it take a little bit of geometry to work out that this D spacing is around 0.6 of A. A is the cube side length of this so there was a question last time about AB and ABC structure. This is just remind you of what they are to clean up a little bit. So the closest packed structure, you can pack it in two different ways. So this is a closest packed structure. So if you have the way you pack things is if you have a layer, you arrange your atom in a triangle kind of thing like this. So this is my first layer, right? And the shaded area will be my second layer. So that's okay, right? So that's 2 layers. So that's AB structure. The third layer, if I want to stack the third layer on top of these two, I have a choice. I can either stack it directly on top of the open circle, right? So I would have AB structure. So now the third layer, I can stack it here, or I can stack it in this red empty space here. So in between, you see, in between these 3 atoms, and this space is not directly on top of the open circle. So this will be an ABC type structure, okay? And the ABC type structure give you the so-called cubic closest packed structure, which is equivalent to phase center cubic. As if you rotate your part of your crystal, it will become like this. If you just have the AB structure, that will be just hexagonal closest packed structure, which will be just like graphite. So it will be just like this. So this will be your AB structure, right? Because you have this atom directly on top of this one, and so when it doesn't look quite like it, but they are. So this is stacked in this way. Okay, so that's the question about this AB structure. I think people may remember from the first year chemistry about how you stack this AB structure. It's the closest packed structure. It's the densest you can make in terms of the density of the material that you can pack into a cubic or hexagonal